Good morning, everyone. Myself, Dr. Krishnamurthy, working as Assistant Professor in the Department of Chemistry, JSS Arts, Science and Commerce College, Gokak, which is affiliated to Rani Chennamma University, Belagavi. So, this is a third video on the chapter Electronic Spectrum. So, in the last class, we already know about the concept of potential energy curves for bonding and antibonding molecular orbitals and energy level diagram, then qualitative description of selection rule, that is types of selection rule, that is spin selection rule and Laporte selection rule, or it is also called symmetry selection rule. So today we learn about the types of electronic transitions. So the types of electronic transitions. So as we know, when a molecule absorbs energy in the visible or ultraviolet region, an electron in the molecular orbital is excited from lower energy, that is ground state, to higher energy, that is excited state. So an electron may be sigma or pi or n. So sigma electrons in saturated compounds, pi electrons in unsaturated compounds, and n electrons in non-bonded electrons. So these are the possible electronic transitions. So number one, sigma to sigma star transition, pi to pi star transition, n to sigma star transition, n to pi star transition, sigma to pi star transition, pi to sigma star transition. So these are the possible electronic transition. Among these four are very important. They are allowed transitions, and these two are forbidden transition. So these occurs in theoretical. So let us discuss one by one in detail. Before that, this is a graphical representation of electronic configurations, that is energy level diagram. So this is a bonding sigma orbital to anti-bonding sigma star orbital transition. Similarly, bonding sigma orbital to anti-bonding pi star orbital. So bonding pi orbital to anti-bonding sigma star orbital. Similarly, n to sigma star, pi to pi star, and n to pi star. So this is the energy level diagram, shows the possible electronic transitions. So first one, sigma to sigma star transition. So it is nothing but a sigma electron from orbital, that is bonding molecular orbital, is excited to corresponding anti-bonding orbital sigma star, that is called sigma to sigma star transition. So it is a high energy process since sigma bonds are very strong. So the organic compounds in which all the valential electrons are involved in the formation of sigma bonds do not show absorption in the normal UV region, that is 180 to 400 nanometer. So the energy required is large for this transition. So for sigma to sigma star transition, the energy required is large. So for example, the saturated hydrocarbons like methane, it has a CH bond only, and it can undergo sigma to sigma star transition, and it shows absorbance maxima at 125 nanometer. So next, second one, pi to pi star transition. So nothing but pi electron in a bonding orbital is excited to corresponding anti-bonding orbital pi star, that is pi to pi star transition. So this type of transitions occurs in the unsaturated centers of the molecule, that is in compounds containing double or triple bonds, and also in aromatics. The excitation of pi electron requires smaller energy, and hence the transition occurs at longer wavelengths. The compounds containing multiple bonds like alkenes, alkynes, carbonyl, nitriles, aromatic compounds, etc. undergo pi to pi star transitions. So alkenes generally absorb in the region 170 to or 205 nanometer. So next one, N to sigma star transition. N to sigma star transition. This type of transition takes place in saturated compounds containing one heteroatom with unshared pair of electrons, that is n electrons, like oxygen, nitrogen, sulfur and halogens are capable of n to sigma star transition. So these transitions usually requires less energy when compared to sigma to sigma star transitions. For example, halides, alcohols, ethers, aldehydes, ketones, amines, etc. So the number of organic functional groups with n to sigma star peaks in UV region is small when compared to sigma to sigma star transition, that is 150 to 250 nanometer. So next one, n to pi star transition. Here an electron from non-bonding orbital, that is n, is promoted to antibonding pi star orbital, that leads the n to pi star transition. So this type of transition requires the least amount of energy out of the remaining all the transitions, and hence it occurs at longer wavelength. It contains organic groups. So the compounds containing double bond involving heteroatoms, that is CO, C triple bond and NO, undergo such transitions. So N to pi star transitions require minimum energy and show absorption at longer wavelength around 300 nanometer. So next, sigma to pi star and pi to sigma star transitions. So as we know, these electronic transitions are forbidden transitions and they are only theoretically possible. Thus, N to pi star and pi to pi star electronic transitions show absorption in region above 200 nanometer, which is accessible to UV visible spectrophotometer. The UV spectrum is of only a few broad of absorption. So this is about the types of electronic transitions. So next, the very important Franck-Condon Principle. So this is a very important concept to the point of examination. So Franck-Condon Principle. So generally the electronic transitions are governed by Franck-Condon Principle. So before we go to the statement of Franck-Condon Principle, let us know about the Maxwell-Boltzmann's distribution law. So at normal temperature, most of the molecules reside in zero vibrational level. This information is easily obtained from the Maxwell's Boltzmann distribution law. So mathematically it is represented n by n naught is equal to e to the power of minus delta E divided by RT. So according to Boltzmann distribution law, the distribution of the molecules between ground state and also the exit state, the low energy state is ground state represented as n naught, and the higher energy state is exited state represented as n. The population of ground state is more than the transition from ground state to exited state is most probable transitions. So transitions are also exited state. Transitions are also governed by the population in the ground state and in the exited state. Here the delta E is the energy difference between two energy levels. So the population is controlled by thermal energy. So it is evident that the population is controlled by delta E by RT, where RT is the thermal energy. That means if the temperature is low, the molecules cannot jump from ground state to exited state. So the population of ground state will be more. If the temperature is high, the molecules can jump from ground state to excited state, then the population of ground state will be less. So the ratio of population between ground state and excited state, and the temperature, and the difference between the energy levels, these are the important factors governed by the Maxwell's Boltzmann distribution law. So next, so here we observe two curves. So one is ground state, and ground state with lower energy, and the other one is excited state with higher energy. And here observed a horizontal lines or waves represents the vibrational energy. Here horizontal lines represents the vibrational energy, and then the V is equal to 0 level is the most probable transition. So the wave function for 0 vibrational level has a maximum in the center, indicating the region of maximum probability according to the potential energy curve. So therefore, most probable transition during the act of light absorption is that which originates from the center of V is equal to 0 vibrational level. So next, if you supply energy for any electronic transitions, it is also accompanied by vibrational and rotational transitions. This we already know. So because energy required for vibrational and rotational will be less when compared to electronic transitions requires more energy. So when compared to vibrational and rotational transitions. So the time taken for an electronic transition is of the order of 10 to the power of minus 15 second, and the time required for vibrational transition is about 10 to the power of minus 3 second. So which is nearly 10 times as slow as electronic transition, or electronic transition is 10 times more faster than the vibrational transition. So here the internuclear distance do not change, that is the nucleus will not change its position and the momentum. So during the electronic transition the internuclear distance do not change. This is very important. The internuclear distance do not change by the act of light absorption. Hence transition process is represented using a vertical lines. So electronic transitions are represented as vertical line because there is no change in the internuclear distance, so which is parallel to the potential energy axis and originates from lower potential energy curve to higher potential energy curve. So here we observe there are two potential energy curve. Among these, in the first diagram the transitions are in vertical lines, and in the second the transitions are not vertical, they are slanted. So among the two, which is electronic transition? So the answer is the first one, because according to Franck-Condon Principle the electronic transitions always written in vertical lines or vertical transitions, because electron transitions are very fast. It requires 10 to the power of minus 15 second, whereas vibrational transitions requires 10 to the power of minus 3 second. So here the position and the momentum of the nucleus will not change. Therefore the electronic transitions are written in vertical lines. So next, Franck-Condon Principle. So this is the statement, very important. This fact forms the basis for the formulation of Franck-Condon Principle, so which is stated as follows. An electronic transition is so fast, that is 10 to the power of minus 15 second, when compared to the nuclear motion or the nuclear uh, distance or vibrational motion, 10 to the power of minus 3 second, that during an electronic transition the vibrating molecule does not change its internuclear distance. So this is very important statement. So an electronic transition is so fast, that is about 10 to the power of minus 15 second, compared to the nuclear motion or vibrational motion, that is 10 to the power of minus 3 second, that during an electronic transition the vibrating molecule does not change its internuclear distance. That is, the nucleus has some relative position and momentum as before the transition. As before the transition. So here, shapes of absorption bands. So this represents the application of Franck-Condon Principle. So we can find the shapes of absorption band. So here there are three cases. So in the first case, the transition takes place from V0, V is equal to 0 to V is equal to 0. So 0 to 0. So this is most probable transition state. So here, ground state to excited state, V is equal to 0 to V is equal to 0. So this is most probable transition. The intensity of this transition is more. So in the second case, in the second diagram, the transition takes place from V is equal to 0 to V is equal to 2. Here the intensity of the transition is less when compared to the first diagram. So when come to the third diagram, the transition occurs from V is equal to 0, V is equal to 0 to V is equal to infinity. So that is towards the dissociation energy. So here we not observed electronic spectrum, here we observed a continuous spectrum form. So due to the transition from V is equal to 0 to V is equal to infinity. So that is in the first case, first diagram, most probable transition appears as the most intense absorption line, that is transition from V is equal to 0, that is V is equal to 0 to V is equal to 0. And in the second one, few transitions are also possible from the other positions of V is equal to 0 level, adding to the width of the absorption band. In the third diagram, if the transitions occur to a position corresponding to energy greater than the excited state, that is the dissociation energy, the molecule dissociates directly on excitation. So discrete vibrational bands are not observed. Instead, we observed a continuous spectrum. So this is about shapes of absorption band. So very importantly, Franck-Condon principle is very useful in investigating the vibrational structure of electronic spectra. So in this class, we'll learn about the types of electronic transitions, that is sigma to sigma star, n to sigma star, pi to pi star, n to pi star, and so on. Then very important, Franck-Condon principle and their applications. Thank you.